Havar is at the dog park with Roscoe, his Labrador retriever. Roscoe catches a scent of interest and walks 29.5 meters south, then 21.7 meters at an angle 31.9 degrees north of east, and finally 40.8 meters west. And in this question, we're asked to solve for the magnitude and direction of Roscoe's total displacement. The first step to solving any vector addition problem is to draw a good diagram. Pause the video and draw a diagram for yourself before proceeding. To begin, I'll show the first vector, 29.5 meters directly south. Our second vector, 21.7 meters at an angle of 31.9 degrees north of east. And then our last vector, 40.8 meters directly west. So if I've drawn my diagram well, then I know that my resultant vector r will look something like this. Now, to go about quantifying the magnitude and direction of this vector, we'll want to first break all vectors into their individual horizontal and vertical components. We'll call our first vector here in red A, our second vector in blue B, and our last vector in yellow C. I've gone ahead and blown up this diagram so it's easier to see, and also drawn in a table down below to keep track of the x and y components for each of my vectors. I recommend you do this whenever doing a vector addition problem. If we look at vector A, we'll see that there actually is no x component for vector A. Anytime we have a vector that is perfectly horizontal or vertical, it's just an x or y component by itself. And so in this case, the y component for A would be the negative 29.5 meters. And notice I made this negative. And remember, anything pointing down or to the left, we're going to call negative. And then anything pointing up or to the right, we're going to call positive. So please make sure, this is the number one thing I see is students forgetting to keep track of their negative and positive signs. So remember, AY here should be a negative 29.5. If we take a look at vector B, I'll go ahead and draw in the x and y components here. This is BX and by, and my theta value here was 31.9 degrees. So we see here that if I'm looking for bx, I can use my trigonometry here. That would be cosine 31.9 degrees is equal to b sub x over 21.7, which means that my b sub x is 21.7 times cosine 31.9 degrees, right? And then my b sub y would be very similar. It is the opposite side of the angle that I was given. So sine of 31.9 degrees is going to be b sub y over 21.7, right? Opposite over hypotenuse. So that means that b sub y is going to be 21.7 times sine 31.9 degrees. And I know these are both going to be positive, right? Because this one's pointing to the right and this one's pointing up. So I'm good. They're both going to be positive components. Now, if I look at vector C, I'll see that vector C only has an x component. It does not have a y component because it is horizontal. So the x component for vector C is negative 40.8 meters. And again, negative because it is pointing to the left or west in this case. So my y component here is 0. Okay, now I'll go ahead and add all of these components to my table. And now I'll go ahead and add all of the x components separately and then the y components. That will give me a resultant vector of negative 22.4 meters in the x direction and then negative 18.0 meters in the y direction. Okay, so now that I've solved for the x and y components of my resultant vector, I can go ahead and find the magnitude using the Pythagorean theorem and the direction using tangent inverse. Pause the video and see if you can solve the rest here on your own before proceeding. I've gone ahead and copied our table over to a fresh workspace. So when I'm looking for the resultant vector, I will always draw my resultant vector triangle using the x and y components. And so in this case, because they're both a negative, I know that I'm going to draw my triangle like so. I'll begin with a x component pointing to the left and a y component pointing down, which means that my resultant vector looks something like this. And so this would be my rx, this is my r sub y, and this is my r. And so now to solve for the magnitude of r, I can go ahead and use the Pythagorean theorem. Again, that is r is equal to the square root of r sub x squared plus r sub y squared. When I plug in values, that would be r is the square root of 22.4 squared plus 18 squared. And notice whenever I do the resultant vector, I drop the negative signs. Now that I've accounted for the direction, I can leave out the negative sign. It'll just make our calculations more complicated. So that means that my resultant vector is equal to 28.7 meters. And it's important to keep in mind that I did not use these values when I did my calculation. I actually used the entire value from my calculator. So again, make sure you don't include rounding error when you do this. I would include these values to at least 3 or 4 decimal places if you're going to do it by hand, or if you're going to store these values in your calculator, you can make sure you get perfect results. Now that I know this is equal to 28.7 meters, I can go ahead and solve for this theta value right here. So I'll go ahead and say that tangent of theta is going to be equal to the opposite side over the adjacent side. And in that case, that would be 18 over 22.4, again, using the exact values. That would mean then theta is tangent inverse of this fraction. And putting that into my calculator, I get a degrees of 38.9 degrees. And to report this using my compass directions, I'll just show in a reference axis over here. So I'll just show in, this is my north-south, this is my east-west. And so I see that this theta value right here, this angle, is actually going towards the south, starting from the west. And so I'll report this as 38.9 degrees south of west, right? We always go towards the first one, and we start at the first direction. So this would be 38.9 degrees south of west. So I would report this as 28.7 meters at 38.9 degrees south of west. And that would be my final answer for the total displacement, both the magnitude and direction. Now, the last part of this problem asked us to solve for Roscoe's average speed and velocity given that his trip took 80 seconds. Recall that the formula for average speed is the total distance that an object travels divided by its total time. And in this case, the total distance that Roscoe travels would actually be found just by adding up each of the segments of his motion. So 29.5 meters plus 21.7 meters plus 40.8 meters, right? Distance doesn't care about direction. And that would all be over 80 seconds. And that would be 92 meters over 80 seconds, which will give us an average speed of 1.15 meters per second. And I'll go ahead and box that. Now, for average velocity, recall that the formula for average velocity is total displacement over total time. And in this case, I've already done the hard work of calculating my total displacement. That would be the magnitude of my resultant displacement vector. So his velocity would be 28.7 meters over 80 seconds. And that'll give me an average velocity of 0.36 meters per second at 38.9 degrees south of west. And again, recall, because velocity is a vector, right, it uses displacement, also a vector, velocity will inherit the direction of the displacement vector. And so I'll just take that 38.9 degrees south of west with me when I calculate the average velocity of Roscoe. Okay, so you've now seen an involved vector addition problem with an additional task of calculating speed and velocity. You should be ready to go now and move on to the next module for projectile motion.